All right, we're moving on to solids of rotation. There's two different methods. We're going to look at what's called the disk method first. So if we have some region R, this region is in quadrant 1. It's bound by the graph y equals 5 and y equals x squared. Its vertex we know is at the origin, and it's also bound by the y-axis. So if we were to take this region and rotate it around an axis, that would create a solid. So like if I take this and rotate it all the way around the y-axis, I'm going to get this solid. And this particular solid, if you take Calc 3, this will come up. It's called a paraboloid. Paraboloid. I'm not sure if that's an O or I think that's an A. Paraboloid. Teach math. Not so good at the spelling. So that's a paraboloid. And each slice of the paraboloid, each cross section of it, is a disk. And a disk is another, like a disk is going to be a circle. If you think about a frisbee, we sometimes call those disc golf. You are too young for this, but when I was growing up, music was on a CD, a compact disc. So a disc is a circle. So if I look at these cross sections, same as before, like as we're closer to the base of the paraboloid, the discs are smaller, they get larger as we go out, but we can still integrate them to find the volume of the solid. So all of the discs are going to be circles, and we know the area of a circle is pi r squared. So the volume, using the disk method, in this case, these are going to be dy disks because our disks are perpendicular to the y-axis. So your disk is always going to be perpendicular to the axis of rotation, and your axis of rotation tells you also if it's dy or dx. So our volume is going to be, we'll integrate pi times the radius squared, and our radius will have to be in terms of y. And then we said this is again a dy slice, so our disks are dy. And we would integrate this one from 0 to 5, going back to that original problem. And so I'm not going to do this particular one, but as you can see, we could always pop out the pi and put it out front since pi is a constant. So as we get down here to the box that shows us the disk method, these are essentially the same. One is for when you have dx slices. So like let's say that you have something like this. Those disks would be dx, and then the ones above are dy. All right, so let's actually just go jump straight into this first example. So find the volume of the solid generated by rotating the region bound by y equals the square root of x. So I'm going to sketch y equals the square root of x equals 4, and the x-axis. And we're going to rotate this around the x-axis. So here's my region. I'm just going to shade it in. And we're going to rotate it around the x-axis. So if you can imagine what that shape is going to look like. So since we're rotating around the x-axis, we're going to be working with dx slices or dx disks, and we really need to draw in one single disk. All right, so we said that when we're drawing in the disk, I'm gonna kind of draw a front-facing disk this way. I guess that doesn't look like a circle. We know we need the radius. This is like the x-axis coming through here. So I've got to think like, all right, how long is my radius? Well, in this case, if I imagine from the x-axis up to the curve, because this is the x-axis, my radius is just going to be the square root of x. But we should really think of it like we've been discussing in previous examples as top minus bottom. So my radius is going to be the top function, the square root of x, minus the bottom function, and that's y equals 0, so minus 0. Therefore, my radius is the square root of x. All right, so when we find our area, we're going to use that radius. All right, so for our volume, we know it's going to be pi r squared, but I'm going to pop the pi out in front of the integral since it's a constant multiplier. And we are integrating from 0 to 4. So from 0 to 4, those are our limits. They're x values because we're working with a dx slice. And then we said pi times the radius squared, and that our radius is the square root of x. All right, so this is the formula we're working with. All right, so I'm going to keep the pi out in front, and luckily the square root of x squared is just x. So we could jump straight into the antiderivative. The antiderivative of x is just 1/2 x squared, and we're going to evaluate that from 0 to 4. So I'm going to keep pi out in front. 1/2 times 4 squared. I really could pop the 1/2 out, but whatever, I already wrote it. 1/2 times 0 squared. All right, 4 squared we know is 16, so we get pi times 16 over 2, 16 halves, and then that's minus 0 halves. So 16 over 2 is 8. Our volume is 8 pi. All right, so what I really want you to do is pause the video, try this next example by yourself. It is very similar. The only thing different is you're gonna rotate the region around not the x-axis, but around the line x equals 4. So pause the video and try this one. All right, so I told you to try this one on your own, but it's kind of hard, so sorry if you tried it and got stuck. When we take the region that we had from the last example, but we're rotating it around the line x equals 4, it's going to rotate kind of like the example on page 111 that we're looking at. So we're going to get dy discs again, and the radius, I want to think of that from x equals 4, from that line, going out to the edge of the disc to our original curve. Now, because these are dy discs, I know everything needs to be in terms of y. So our original curve right here was y equals the square root of x. We need to square both sides to solve for x and use x equals y squared instead. So remember, we always go right minus left. So my radius is going to be 4 minus that curve, which is y squared. All right, so that's our radius. So again, if we think about what we're going to integrate, the volume is going to be pi r squared. I'm going to pull pi out because it's a constant multiple. My radius is going to be 4 minus y squared in parentheses squared because that's just the radius. And then I know these are dy slices because they are perpendicular. The discs are perpendicular to the y-axis. So the only thing I don't know are my limits of integration. And I need my lower and, like, when I say lower and upper, I really mean my lower and upper because these have to be y values. So my lower limit is going to be 0 because the x-axis is the boundary. My upper limit is going to be right here, whatever y is when x equals 4. So just plug that in. If y is equal to the square root of x and x equals 4, the square root of 4 is just 2. So from 0 to 2. All right, so the rest of this is just arithmetic, really. I mean, I guess calculus, because we have to find an antiderivative. I'm going to expand that polynomial. I'm going to FOIL it, and since I'm squaring it, I'm just going to use that pattern. So I'm going to square my first term. 4 times 4 is 16. Then 2 times 4 times negative y squared. I'm going to have a negative 8y squared as my middle term. And then my last term, square that, would be y to the 4th. All right, so that was just algebra. Hopefully I did that step correctly. I'm sure you'll let me know if I didn't. All right, so now we want to find the antiderivative. So pi comes along for the ride. 16 becomes 16x. Negative 8y squared. Oh no, does not become 16x, excuse me. Forgot we're doing this with respect to y. It becomes 16y. Negative 8y squared becomes negative 8 thirds y cubed, just using that power rule there. And then y to the 4th becomes plus 1/5 y to the 5th. Yeah, this example is way less fun than the last one. I guess, or more fun, depending how you look at it. All right, so this is what I got for the antiderivative. So we're gonna now plug in the upper limit and the lower limit and find the difference. So I'm gonna keep pi hanging out along for the ride. 16 times 2 is just a 32. 2 cubed is 8. So negative 8 thirds times 2 cubed, 8 times 8 is 64. So negative 64 thirds. Let's see, 2 to the 5th. I always forget, is that 64 or 32? 2, 4, 8, 16, 32. So that becomes 32 fifths. And then minus, when we plug the 0 in, we just get 0 for all of that. Thank goodness. All right, so all we really need to do is find some common denominators and then, carry out the simplification and then tack a pi on. All right, I'm not gonna lie, I paused the video and did that in the calculator because I didn't feel like doing it. I believe we should get 256 over 15 times pi. Hopefully I did that correctly in the calculator. So I'll double check it in just a second.